Okay, let's have a look at example 1 on page 66 of the textbook. This is a wonderful exercise and its solution is beautiful, so this is the reason why I wanted to make a short video, because this is an interesting control problem and the solution is wonderful, as I have just mentioned. So let's start with the details. We have a first order linear ODE, ordinary differential equation, that describes how the system behaves, in which ut is the control variable, and in the exercise we are looking for an appropriate control function ut with the minimum norm. So this is what we are looking for is a minimum energy function. Okay, so let's start with the boundary conditions. We have a variable called theta. This is the initial condition. Supposing that theta in time t, which we call the angular position of the motor shaft, is the time integral of the function omega. Okay, from which it follows that theta at time 0 must be 0 because this set is empty. Okay, so this is one condition. This is an initial condition. Another condition, boundary condition, a terminal condition, requires that in time t, at the end of the process, theta, the angular position of the motor shaft, must be 1. So we integrate omega between 0 and 1, and it is equal to 1, plus omega at time 1 must be 0. So these two equations are the terminal conditions. And these two requirements are the initial conditions. All right. So the problem from a state of rest we go to a state of rest. So initially the system is at rest, and finally the system is at rest again. Okay, we have this differential equation, which is interesting, and important, so let me write it down again. We can describe its general solution. So to find the general solution, you can use the textbook by Martin J. Osborne, Mathematical Methods for Economic Theory. So if you are not familiar with the general solutions of differential equations, just have a look at that textbook. It's very instructive. It's amazing. So by using the way Osborne describes the general solution of this problem, we have the following solution. of course, we know nothing about the function u. The constant is a real number. After expanding this solution, we will receive c times e yes plus this integral. Okay, it's just ordinary expansion. So, the end point of the problem, so the starting point is of course 0, and the end point is 1. Okay, so let's use the boundary conditions. Our goal at this point to find restrictions on u. So let's use the boundary conditions. First, we know that omega at time 1 is 0. So let's use the general solution at time 1. The upper bound is 1, es us ds. This is 0. This is 0. Because finally we are in a state of rest, and we can put this term behind the integral sign with no problem. So we will have this equation. Okay, this is easy. This is easy. So this is one condition, one restriction on ut. Note that there is an unknown parameter in the equation. Likewise, we can use the other condition. This is the initial condition, because in 0, so we use the same general solution we described by the use of the Osborne textbook. This is also 0 from the initial condition. And note that this must be 0. This is 0. So, at the end of the day, this is all we have. So, this is 0. This is 1. So, at the end of the day, the constant term is 0. This is an important result. So now, we can rewrite the first restriction on the function u, because c is 0, so all we have is this integral, which is 0. All right. This is equation 1. Let's call it equation 1, okay? Because this is a very informative restriction on u, on function u, this part of the equation. All right. We have, again, we have this differential equation. We have this differential equation. We also know that the time integral of the function omega is the function theta, and from this equation the time differential of omega is the integrand at the upper bound. So the time differential of theta is simply omega t. Okay, and by substituting this result into the original differential equation, we will have this equation, from which it follows that ut minus the time differential of omega is the time differential of theta. Note that the time differential of theta is not dependent on theta. So from this it follows that we can rewrite the equation in this form. Okay, because we know that we used the previous results. So given this equation, the time differential of theta is going to be the integrand at t. So we use the same elementary result in calculus. This is the difference of two integrals. So we can also say, so we can integrate it by parts. By which I don't mean partial integration. So this is a sum. Okay, so from the linearity of the integral. Okay, and we know that by the same elementary result in calculus, it is equal to omega t minus omega 0, which is equal to omega t because omega 0 is 0. Okay, all right, so we have this equation minus omega 1. But omega 1 is equal to this integral at the end of the day. So what we have is theta 1 integrating u between 0 and 1 minus e t minus 1 times ut dt, and we can factor it out. So at the end of the day, and this is going to be our second restriction on ut this is equal to 1. And this is the second restriction. It was equation restriction 1. It is equation 2, or restriction 2. So, to be clear, the restrictions so on the one hand, et minus 1 ut dt 0, yes, and okay, so these are the restrictions we have on ut. So how to proceed? We are looking for this unknown function on which we have two restrictions. So these two restrictions seem to be the inner products of a function space. So see page 48 of the textbook, because it's interesting to realize that in general, what we see is an inner product in this form, right? So this is the inner product of this function space. So now we know that we are looking for a function u in this function space. And now everything is ready, and we can apply theorem 2 on page 65 on the function space L2. So let's rewrite the restrictions. So we have two restrictions, 1 and 2, and let's rewrite these restrictions in the language of theorem 2 of page 65. So this is 0 and this is 1, right? So this is C1 and this is C2, and Y1 is E t minus 1 and y2 is the other function from the restriction. So this is y1, this is y2, right? And this is u. And this is c1, this is c2. That's all. So we are looking for an appropriate ut function from the function space L2 that meets the requirements in 1 and 2. These two requirements. So ut is in the function space L2 and meets these requirements. So, according to theorem 2, the minimum norm, the function with the minimum norm, is in a linear variety. because, please remember, these two restrictions, they define a linear variety. Okay, so to find the function, we need the normal equations. We need the Gram matrix. So this is this integral, which is easy to realize that is equal to this function. Okay. The second function, so we are describing the elements in the Gram matrix. Actually, now we are describing two functions, and by expanding, if you use MATLAB, you can speed up the process, but trust me, you can do this by hand, because we are working with elementary functions. But admittedly, MATLAB helps. Yes, and the final element in the Gram matrix dt is equal to 2 over e minus over 2 minus 1 over 2. So now we have the Gram matrix. This is y. This is the Gram matrix, and now we know all the elements in this matrix. Over 2, the same, over 2, and this is the element from the right lower corner of the Gram matrix. Okay, and the normal equations on this ground we have the Gram matrix equal to this vector C1 and C2, from which we receive these unknown parameters for the linear combination in this form. Okay, and by using MATLAB, so at this point you should use MATLAB unless you want to spend a whole day with the calculations, and you will receive this vector. Okay, e minus 1 over e minus 3, e plus 1 over e minus 3. So we have the parameters, and now we are very close to the solution, because ut is a linear combination of this form, right? And by expanding it, we will have e minus 1 over e minus 3 times e t minus 1. Yep. So we use the functions y1 and y2. This is y2. So this is alpha 1, this is y1, alpha 2, y2, and after a few steps you will receive this function, which is the optimum ut function with the minimum norm that meets the requirements. So, yes, we are done. I love it. It is beautiful.